4.2.1, example 4.2. We talked about the definition of bound charges in a polarized object before in the previous video, so let's go ahead and do an example together. This is example 4.2. The goal here is to find the electric field from that's produced from a uniformly polarized sphere of radius r. Okay, so that means that there are dipoles. The polarization is constant in space, and I'm going to go ahead and align all of these dipoles so that they're pointed along the z-axis, because that's just going to make our life easier. Okay, so they exist everywhere. I'm not going to draw them any arrows again. Then the goal is to figure out what is the field, and the tool we used last time was the potential. So let's first calculate the potential. To calculate the potential, we have two types of bound charges that we can identify. The first is the volume bound charge, and the second is the surface bound charge. Now, the volume bound charge is calculated by the divergence of the polarization, but the polarization is uniform everywhere, so that means that it is zero and there are no bound charges in the volume. Now, what about the surface bound charge? That is the polarization dotted with the surface vector n hat. And I have defined my coordinate system or rotated my object so that the polarization is always in the z hat direction, and n hat is whatever direction is normal to the surface. All right. So I have a polarization vector that is always pointed in the z hat direction, and I have n hat vector, which I could redraw as going all the way through the origin, right? And because of that choice of the coordinate system, I can rewrite that as p times the magnitude of n hat is 1 times the cosine of the angle between them, but that is the polar angle theta. So it's cos theta. So p cos theta is my surface charge density, sigma b. There's already been an example problem done in the book. I can't remember if the video is covered or not, but in example 3.9, we found the potential from something that had this kind of charge density associated with it. Okay, so let's just draw what that looks like. When theta is 0 at the North Pole, you have a lot of positive charges. And at the bottom, when theta is pi, cosine of something near pi is -1, so we have a lot of negative charges. So it looks kind of like a big dipole in that instance. A lot of negative charges at the bottom, a lot of positive charges at the top. So example 3.9 says that the potential is P r over 3 epsilon naught times cosine of theta when we are looking inside our sphere, and it is P r cubed over 3 epsilon naught 1 over r squared cosine theta when r is outside. Right, and we know that potentials are continuous at surfaces, so I can even write when it's greater than or equal to capital R. Okay, so let's first look inside. I have the potential being P over 3 epsilon naught. I'll write R cosine theta together because I'm going to go ahead and say that, well, R cosine theta is really just Z. So that's P Z over 3 epsilon naught. And I'm going to go ahead and calculate the electric field inside by taking the negative of the gradient of that potential. I have something that depends only on a Z, so I'm going to take this in Cartesian coordinates to make my life easy. That is minus P over 3 epsilon naught dz dz, and the Z hat, which is minus P over 3 epsilon naught, and the Z hat. So the field inside is constant. That's pretty cool. And then outside, my potential is equal to P R cubed over 3 epsilon naught 1 over R squared cosine theta. And I'm going to throw in some extra terms that are going to seem unnecessary at first. But I'm going to put pi over pi, right? I'm just multiplying by 1, so that's fine to do. I'm going to go ahead and put a 4 over a 4. Okay. Let's see if I added those terms in correctly. That I can go ahead and rewrite as 4/3 pi R cubed. Yeah, okay, I think I did that correct. 4/3 pi R cubed times the polarization P times what's left. 1 over 4 pi epsilon naught 1 over R squared times cosine theta. All right, I think I did that correct. Still, what is the volume of my sphere times my polarization? My polarization. Well, it's just since the polarization is a dipole moment per unit volume, that is just the dipole moment, the total dipole moment of my sphere. So that's P over 4 pi epsilon naught 1 over R squared cosine theta. All right, now this is not capital P anymore. It's the dipole moment of my sphere. Remember how we said it looked like a dipole here? Okay, I can rewrite this as a dot product of P with something that gives me cosine theta. That something is going to be my R hat vector. P dot R hat over 4 pi epsilon naught 1 over R squared. So outside, the potential looks just like a dipole. It's just like a dipole, the total dipole moment defined by the polarization.